Hi there. So, if you remember earlier, we were talking about local extremes and intervals of change, but we didn't get to very many examples, so I wanted to do a few more examples. All right, so let's just start here, and let's say I have f of x is 3x plus 1 times e to the 2x. And I want to find, first thing I want to do is find the critical numbers. All right, so remember how we find critical numbers. We set the derivative equal to 0. All right, now some people will just go here and now start finding the derivative. That's the way I'm going to do it. Some people, especially in calculus class, they know they're going to need the derivative, so even before they start doing anything, they just go and find the derivative from the get-go. That's kind of up to you. All right, now beware. Now we're assuming that you're experts on taking derivatives, so you need to look at this. Remember, you need to identify its form first, okay? And so the form of this thing is we have a multiply right here, so we're going to use the product rule. All right, so to use the product rule, you can write it out. That's kind of up to you. If you want that step in there or not. Okay, so then we actually find these derivatives. All right, and so just to save myself a little bit of room, I'm going to go ahead and erase this because I'm going to need this whole slide area. Okay, so I do the derivative of 3x plus 1, that's 3, and then I leave the right one alone. All right, plus, and then I leave the left one alone, and I do the derivative of e to the 2x. Derivative of e to the 2x is itself times the derivative of the exponent. And now I'm setting this equal to 0. All right, so I'm supposed to solve this equation now, okay? And so to solve this equation, this looks pretty complicated. And so if you remember all term, I've been trying to get you used to factoring in most cases. All right, and so this equation will be a lot simpler once I factor. And if you notice, whenever we're factoring with one of the rules, either the product or the quotient rule, we're looking around the sign in the middle. In this case, it's a plus. With the quotient rule, it's a minus. And you're just saying, is there anything that's the same over here and over here? All right, that's a factor, something being multiplied. And the only thing that is this e to the 2x right there. So I'd factor out that e to the 2x. All right, whenever I factor e to the 2x out of this first part, all that's left is a 3. And then whenever I factor the e to the 2x out of the right part, I have a 2 left times 3x plus 1. Okay, like that. And then that's equal to 0. All right, so now I have this equation. I probably want to clean up the part inside the parentheses before I do anything else. And so I have 3 plus 6x plus 2 equal to 0. And then I have some like terms there. 6x plus 5 equal to 0. Now, if you remember, the whole point of factoring is the idea, that game that I joked around about one day. If I am multiplying two things and I'm getting 0, then one of them have to be 0. So you just set each factor equal to 0. So right here I have these two factors. I have e to the 2x, so I would set it equal to 0. And then I have my second factor is 6x plus 5. I set it equal to 0. Okay, so this right part's pretty easy to solve. I subtract 5 and divide by 6, like that. Now this part right here, this will end up being a nice thing just to know if you don't know. So if you think about our normal way to do this, I would take ln of both sides. We did this one day in class. Type this in on your calculator. Pause this real quick if you need to, and type in ln of 0 on your calculator. You'll actually get an error whenever you do that. Okay, it's not possible to take the natural log of 0. So what that tells you is that this part right here, this equation has no solution. All right. So, but that's a nice thing to know too, and it can save you a couple steps having to go through all this. This is an exponential equation, okay? And anytime you try to set an exponential equal to 0, you'll always get no solution. Now that doesn't mean there's no critical numbers, because we did get a solution right here. All right. And so what that tells us is that we do have a critical number, x equals negative 5, 6. So that is critical. Now, one thing I realize I've left off, and this is a downside to doing these problems this way, to, say your derivative is equal to 0 and then find the derivative and keep setting it equal to 0. It might be easy to lose the derivative. So you might want to pause a second and ask yourself where the derivative is in this, because once we get to finding the intervals of increase and decrease, we're going to want to know what the derivative is. All right. So that could be an advantage to whenever you start these problems, to just start with your function and then find its derivative, and then start going through the parts to these problems. But if you look carefully right here is the derivative after we've cleaned it up. So our derivative is e to the 2x times 6x plus 5. Okay. Okay, so I'm just picking up where we left off. Here's our function and here's its derivative. And now we want to find the intervals of increase and decrease. All right, and so what we do is we find we get our critical numbers. Okay, we only have one here. So this is ends up being a little bit nice. So remember how this works is I just make a little chart. I denote my critical number like that. And then I just pick test numbers around each one of my critical numbers. In this case, I only have one critical number. And so I can only go to the left and the right. So here's negative 5, 6. So remember, you can pick any number to the left of negative 5, 6. I'm going to pick negative 1, but we could just as easily pick negative 2 or negative 1052. All right, and then a number to the right of negative 5, 6 is 0. All right, and what I want to do, those are called test numbers. And just to point out too, that's the reason I always circle my critical numbers, because you get in these problems, some of them get pretty complicated, and so then it's easy to forget what's giving me answers. And so these are just test numbers. They won't be part of the answer at all. All right, only the critical numbers will be involved in the answers. All right, so what do? I take these test numbers and I plug them into my derivative and just tell whether they're positive or negative. So you might want to pause and do that. Make sure you can see what happens. But if I plug negative 1 into that derivative, I'm going to get a negative. All right. And if I plug 0 into that derivative, I'm going to get a positive. All right. Now, you can take advantage of knowing extra information you don't need to. What I actually did is I just plugged negative 5, 6 into this. And that's the reason how I did that so quickly. Because I know e to the 2x is always positive. All right. But that requires knowing some extra stuff. So if you know some extra stuff, take advantage of it. Feel free to take advantage of it, but you don't necessarily need to. All right. And then just ask yourself, what is that telling you about the function? That's telling you that the function is, oops, I started to mess up, didn't I? Derivative negative means the function is decreasing, and the derivative positive means that the function is increasing. Okay, and what I usually do is I draw myself a little diagram here to help me answer part C. So that means around that critical number, this function is decreasing and then it's increasing. Okay. Make any sense? All right, so and so what is that going to tell me I have right there in terms of extremas or extremes? That tells me that I have a local min right there. Okay, but as far as the part B answer goes, I give the intervals of increase and decrease. So this thing increases on negative 5, 6 to infinity. and then it decreases on negative infinity to negative 5/6. All right. Let's see here. And so then for part C, we want to classify all local. Be aware too, sometimes these are called relative extrema. It just depends on who's saying it. All right. So whenever we're talking about local extremes, we're talking about a local min and a local max. Okay. And so we've already answered this question here. We have this one critical number and it produces a minimum. So we have a local minimum of negative 5/6. It's occurring at negative 5/6. Now that's the only thing that can happen. So there's only one critical number. It produces a local min, so there's no local max. All right, and then just remember here, a minimum or a maximum is a point on the graph, and so we need the y coordinate. So we're going to plug into f. All right, I should have pre-done that. Negative 5/6. Oh no, trying to hurry here. Sorry about that. Negative 5/6 times 3. I'm typing it into 3x plus 1, and then e to the 2 times negative 5/6. That, with y values, I don't mind if you approximate them. So that's about negative 0.28. You can give the exact there. It actually looks a little weird, but it's fine. Okay, and just make sure you realize these are function values, so I'm typing that into my function. Okay, and then especially if you have access to pretty good graphing hardware, or on your calculator if you're good at adjusting your window. All right, it's always good to check your work from the graph. So yeah, if you look here, this is a graph of f of x right here. Okay, and we said that it decreases up to negative 5/6. Well, negative 5/6 would be right around in here. And so notice that the graph here is going down. Right here it looks really flat because there's a horizontal asymptote and this window is big. And then all of a sudden at negative 5/6, it starts increasing like that. And then what's happening, we have this local min right here. And I mean, it's kind of hard to see, but that's about negative 0.28, its y value. So, okay, so let's look at another one now. Let's look at x to the fourth minus 3x squared. So following my advice from the last example, we might want to, if we know we're going to need derivatives in a problem, we might want to just go ahead and get it out of the way. At the beginning, you might notice here in terms of basic form, we have some linearity going on, and then we just have two basic power rules. So we can apply the power rule to the first one, and then apply the power rule to the second one. Okay, so there's our derivative. So now in part A, if we want to find the critical numbers, we have our derivative equal to 0. Now one thing here, and I don't know why I didn't do that at the beginning too, but you might, whenever you take the derivative, you might want to work on the cleanup then, and then it'll make the equaling 0 part a lot easier. So back up here, if you look, first of all, hopefully you see there's an x in each one of these, so we could factor out an x. But there's also a factor of 2 in all of our coefficients. And so we can actually factor out 2x. And what are we going to get? 2x squared minus 3. All right? So there's the factored form of our derivative. Or if you don't want to do it at the beginning, then you could start here. You don't need this line if you've already cleaned it up. But the key thing is here, you might be saying, oh, we're going to use the quadratic formula. This equation's not even quadratic. It has the third power. All right, so general idea to trying to solve things equal to 0 is you want to try to factor it. All right, and so we have 2x times 2x squared minus 3 equal to 0. All right, and so remember the whole idea of factoring is that then I can set each factor equal to 0. Okay, like that, and this one you divide by 2. One thing to point out too, some of you may have thought we could divide both sides by 2x. The problem is that you're dividing out your variable. And so you can see if you did that, you wouldn't have got this solution, and that's a solution to our problem. And it ends up being a critical number, so we definitely don't want to get rid of it. All right. And then over here you have a couple options. Now that this equation is now quadratic, all right, and so one way to solve this is that with the quadratic formula, A would be 2, B though would be 0, and C would be negative 3. Okay, so you could go through the quadratic formula with that. Negative B plus or minus the square root B squared minus 4 times 2 times negative 3. Sorry, I don't have much space. All over 2 times A. Okay, or if you're missing a middle term there, you can isolate. You just got to remember something. Okay, so we get x squared is equal to 3 halves. All right. But you got to remember we're solving something in the xy plane. We're solving something about a graph. And so whenever I take that square root, I got to make sure and remember to put that plus or minus in front of it. Okay? So we get that. All right, so there's our critical numbers. So there's our answer to part A. Okay, and then so this is just a rehash of what we already know. So now going on to part B, you're basically really doing B and C together, but we'll break it in. All right. So we have in this problem we have 3 critical numbers. So we have negative square root of 3 halves, we have 0, and we have positive square root of 3 halves. So hopefully you're starting to see kind of how things progress. And so these are my critical numbers. Put numbers around those. All right. We want to compute what the square root of 3 halves is real quick, just to give us an idea about what our... So it's about 1.22. So that's about positive 1.2. And this is about negative 1.2. Like that. So that gives us an idea about what to pick for our test numbers. And so that means that we can use negative 1 and positive 1 in here, and then negative 2 and positive 2 out here. You don't have to. Okay, so first to determine where it's increasing and decreasing, we're plugging into the derivative, and then we're going to use that to tell us about what's going on with the function. Okay, so we have, if we plug in negative 2 into this. Now I'm going to show you something here. This is the way actually I learned to do it whenever we had things factored. All right. Now you can just take negative 2 and plug it into this expression and see if it comes out positive or negative. I'm just trying to save some time with my calculator. But I'm plugging negative 2 into this thing right here. Well, if I plug in negative 2 right here, that's going to be a negative. And then if I plug negative 2 into this, that's going to be 4, 8 minus 3. That's positive. So I have a negative times a positive. That gives me a negative. All right. So I'll say negative like I've been doing. Like that. All right. If I plug negative 1, here I'm going to get a negative. And here I'm going to get 2 minus 3 is negative. So I have a negative times a negative. That makes a positive. All right. And then if I plug 1 in, I'm going to get a positive times a negative. All right. And then if I plug 2 in here, I'm going to have a positive times a positive. Like that. And again, I know all the examples we've seen do this, where these things go back and forth. We'll see one in just a minute that doesn't. So don't always assume that they do. Verify whether or not they do. All right. So that means here f is decreasing, and then it's increasing, and then it's decreasing, and then it's increasing. Okay. So the graph goes down and then up and then down, and then down and then up. So here I have a minimum, here I have a maximum, and here I have a minimum. All right. So that means that this thing is increasing on negative square root of 3 halves up to 0, and then union with square root of 3 halves to infinity. And it's decreasing on just the opposite, negative infinity to negative square root of 3 halves, union with 0 to positive square root of 3 halves. That. And then in terms of C, notice that we have 2 local mins, and we have 1 local max. Okay, our local max has x equal to 0. You can see that one. We're plugging 0 into our function. We're going to get 0. Okay, and then if I plug a square root of negative square root of 3 halves in, I computed it, but then I turned my calculator off. I'm going to get negative 2.25. And if I plug positive square root of 3 halves in, I get the same thing. That. And so there's the problem. Now we just want to check it. All right, so here's a picture of the graph, and let's see if things match up. So negative square root of 3 over 2, that would have been about right here. Oops, sorry. That would have been about right here. And here's 0, and here's positive square root of 3 over 2. Okay, so notice that I have horizontal tangents at all those places. So that looks good. And then let's see. I said it's increasing from negative square root of 3 over 2 to 0. That makes sense. And square root of 3 over 2, square root of 3 halves to infinity. That makes sense. Decreasing negative infinity to negative square root of 3 halves. All right. And 0 to positive square root of 3 halves. That makes sense. And then we have these 2 local mins at the square roots, and we have a local max at 0, 0, so everything looks good. Okay, here's another one we want to look at. Basically multiplying 2 polynomials right here. All right, knowing that we're going to need to do find the derivative, let's go ahead and do it now with the product rule. So, this one you can take your time with to help you with each part. And then 2x plus 1 squared times the derivative of x cubed. All right, so key thing is right here we have the chain rule. So we're going to bring down the power, but we keep the inside the same to the first power. Then we multiply times the derivative of the inside. Okay, and then we leave the right function alone. And then same thing here, we leave the left function alone, and we differentiate x cubed, which is 3x squared. Okay, now this one's mostly an example of factoring. All right, so whenever we talk about factoring with the product or quotient rules, we're looking around the sign in the middle. All right, we're looking for things that are the same over here as the same over here. Not exactly the same, but at least the bases of the factoring. So if you look in terms of numbers, there's a 4 here, but there's only a 3 there. So no numbers factor out. Here I have a 2x plus 1 to the first, and here I have a 2x plus 1 squared. So that means I always factor out the lowest power if you're not clear about that. So I just factor out 2x plus 1 to the first. And then here I have x cubed, Here I have x squared, so I factor out the smallest power, x squared. Okay? And then I look at what's left. All right, so I factored out 2x plus 1 to the first times x squared. So I factored this out, but I still have the 2 times 2, which is a 4. All right, and then I factor out an x squared from x cubed. So I have an x left. All right, so that's the left side. And then I factored out a first power of 2x plus 1. Oh, sorry, I didn't think about the number. We have that 3 that didn't get factored out. And then I factored out 2x plus 1 to the first, but there's a square here, so there's a 2x plus 1 left. And then I factored out x squared, so all that's gone. So that's what there's how that factors. All right, and then we can clean up on the inside. Notice that this is 6x plus 3 if I distribute it. So I'm going to end up with 10x plus 3. And there's my derivative. Okay, so now I find the critical numbers. Okay, that's where the derivative is equal to 0. So I have 2x plus 1 times x squared times 10x plus 3 equal to 0. And so I set each one of my factors equal to 0. Right? And then I solve for x in each one. Subtract 1 and divide by 2. Take the square root there. And then I subtract 3 and divide by 10. Okay? Like that. And these are my critical numbers right here. So we found those. Now, if you want to, I talked about checking at the end. If you want, this one's a little bit tricky, and I'm going to show you that in a minute. But, you can look at the graph of this and convince yourself that those are actually critical numbers. This one actually is a little bit different than what we've seen, though, so it might not be that. It might be easier said than done. Okay, so hopefully you saw this. Remember, the idea is that we're plugging each one of those test numbers into the derivative here. And so however you do that analysis, like the way I learned it, or just plugging it straight in. All right, and so notice here, this is a problem where that pattern just doesn't flip back and forth. So first f is increasing, and then it's decreasing, and then it's increasing, but then it's increasing. Okay, so in terms of those little diagrams, increasing then decreasing, decreasing then decreasing. This is a little thing that's hard to describe, but it kind of looks like that. All right, you don't need to overthink that. You just need to draw two sides that are increasing. Okay, but anyway, that means there's a max here, there's a min here, and there's no extrema here. Okay, like that. All right, and so in terms of answering the intervals of increase and decrease, this thing is increasing on Well, for the first place is from negative infinity to our first critical number. So negative infinity to negative zero point 0.5. All right, like that. Where's the second place? It's increasing from here to here. Now, this is going to be one thing that might throw you a little bit. At 0, remember that the derivative was actually equal to 0. So at 0, it's neither increasing or decreasing. So you don't just say that it's increasing from here on out. There's a momentary pause where it stops increasing. So you say negative zero point 0.3 to 0, but then from 0 to infinity. All right. We'll talk about this later, but there's a special geometric point right there called a point of inflection, a horizontal point of inflection. But now this thing is decreasing on just one interval, negative zero point 0.5 to negative zero point 0.3. You might be saying, I thought you said to answer the x values exactly. Why are you using decimals all of a sudden? It's because these fractions are exactly equal to those decimals. Okay. So there's part B. And then to answer part C, we have a local max. It occurs at negative 1/2 or negative 0.5. And then we have a local min. It occurs at negative 0.3 or 3/10 if you want to write it that way. And so, again, pause and make sure you can fill those in correctly because I still need to compute them too. Okay, hopefully you did that. And just remember to get points on a graph, we're plugging into F for each one of those. Surprisingly, they're both 0. All right, now you might be saying, well, what about this point that we left alone? Sorry, I've been using my small dot. I like the big one. This one right here. So there's no local max or min here. All right, it doesn't change from increasing to decreasing. And so we'll worry about that later. We'll talk about points of inflection later, and so we'll end up calling that a point of inflection. But for now, in terms of what we're answering, we just don't worry about it. Okay, I just want to show you one more. I know this is getting a little long, but here we have x to the fifth plus 2x. So if I go and take its derivative, I get 5x to the fourth plus 2. Okay, there's not really a whole lot, there's not anything there I can factor since x isn't in both terms and 5 and 2 doesn't factor. All right, so if I go and start trying to find the critical numbers, all right, then I'm solving the derivative equal to 0. All right, and so that's 5x to the fourth plus 2 equal to 0. All right. Here I have a fourth degree equation, but there's only x to the fourth, so I can isolate here. All right. So one way you can think about doing this is taking the fourth power, or the fourth root of both sides. All right, I'm going to point out something in a minute though. But so over here we get x. Now one thing to point out that I was sloppy about is we did just take a fourth root. That's an even root. I should have put plus or minus out in front. All right, but the thing is here, try to calculate that number. All right, so remember the main way we've talked about handling that is that's the 1/4 power. So take a minute and pause and type that in. Okay, so hopefully you did, but the key thing is is that's not a real number. All right. So even powers act just like even roots. You could have spotted it here. Anything to an even power is going to be positive. So x to the fourth will always be positive, but I'm trying to set it to a negative number, so that doesn't work out. Okay, or you can just go through the steps, but then try to calculate that, and you'll see that it's not a real number. All right, now, so we got to think back to what we're trying to do. We were trying to find the critical numbers here, all right, and we went through some algebra, but we saw that the solution that we try to get is not a real number. So what does that mean in terms of critical numbers? All right, that means there's no critical numbers. All right, so we've answered part A, so we don't need to overthink that. So part B starts looking really tough because we're used to making a chart and then using and then going to the critical numbers and making numbers around them. But there's no critical number here. So what does that mean? That just means that this function never changes behavior. Okay? And so whenever there's no critical numbers, that means that this thing is always increasing or decreasing. All right? So what that means is that I can use any test point to determine whether or not it's increasing or decreasing. All right? And so the easiest number to me is to use 0. All right? And then I plug that into the derivative. All right, my derivative is 5x to the fourth plus 2. So if I plug 0 into that, I'm going to get a positive, like that. All right, but it's always positive or it's always increasing or decreasing. So first of all, that positive means that f is increasing. So that means that f is increasing on what? Negative infinity to infinity. So whenever you don't have critical numbers, it's actually extra nice because you don't have anything to deal with. All right? And then lastly, since there's no critical numbers, and this thing is always increasing, that means that there's no local extrema. All right? So it actually ends up being a little bit simpler whenever there's no critical numbers. It just requires a little bit more thinking. So then if you're confused and wondering what the heck is going on here, just make sure to look at the graph. Typed in this into GeoGebra, there's the graph, and so if you think about it, no matter where you're at on the graph, you're always increasing. You get that little weird point right there, but still, the function's always increasing. So our algebra aligns with what's going on the graph. Okay, so I'm going to leave it there. I hope that helps, and we'll look at some more detailed information about this on Monday.